Okay, CS 161, Lecture 7, cryptographic hashes and max. Woo! One thing I learned about doing that is that you have to make your voice kind of slowly go up and up and up until it hits the climax, because that's what Dan Garcia does when he does this shtick. So you have to say CS 161, Lecture 7, cryptographic hashes, and that's how it works. Okay, so that's what I learned. I'll give you some more entertaining shticks last or next week or something. Okay. So the announcements are basically the same as yesterday. Homework 2 is out, Project 1 is out. If you haven't gotten started, now would be a really good time to get started because it's coming up pretty quickly. And again, next Monday is a holiday, so no lecture, no discussion, no office hours. Okay. So last time we talked about block ciphers, and we said that a block cipher has an encryption function where you input a k-bit key, input an n-bit plaintext, and you get n-bit ciphertext. And then decryption is the inverse of that. So again, you input this key, and then you input the ciphertext, and the output is the n-bit plaintext. And we said to make the block cipher correct, once you have a fixed key, the function should be bijective. So every input maps to exactly one output. That way you can always decrypt. Then we said that if you don't have the key, this function basically looks like a random permutation. So if I gave you a box that outputs block cipher outputs and a box that outputs a random permutation, you can't tell which one is which. We also said that you can try to brute force a block cipher by feeding it every possible key, but that's going to take astronomically long. Like the universe will no longer exist by the time you're done, so don't count on that working. And we said that the algorithms use XORs and bit shifting to be very fast. The modern standard is AES. And then we said block ciphers aren't perfect because, well, first of all, they're not NCPA secure because they're deterministic. So if you feed in the same thing twice, you get the same output twice. So that leaks information if you've encrypted the same thing twice. So it's not NCPA secure. And it can only encrypt n-bit messages. So if my messages are shorter or longer, block ciphers just do not work. So the next thing we did was start chaining block ciphers together to make more complicated modes. So the ones that we came up with were ECB mode, which was the most basic one, and that's not NCPA secure because it's still deterministic. Then we came up with CBC mode, where you chain the output of one ciphertext into the next plaintext block. And that one is NCPA secure if the initialization vector, the IV, is random and not reused. So as long as you pick IV randomly every time, then you have NCPA security. We talked about whether it's parallelizable, whether you have to pad plaintext so that it's a multiple of the block size. And also, if you reuse IVs, you can see that messages start with identical blocks if they do. Then we talked about CTR mode, which is our second one. This one basically said, let's use the block ciphers to create the key to a one-time pad. So I take a random nonce, I feed it through the block cipher repeatedly with different counters. So I get lots of just random looking output, and I use that as the key to a one-time pad. So to encrypt, I just XOR the pad output with the plaintext, and to decrypt, I just XOR the block cipher output with my ciphertext. So that's counter mode. Again, if you don't reuse the nonce or IV, it's NCPA secure. If you do reuse the nonce, then you're basically reusing the key in a one-time pad. So you're out of all security because you're leaking lots of information. And we also talked about making it parallel and also whether you have to pad. And then we kind of glossed over it, but again, remember, these are symmetric encryption schemes, so there's no integrity and no authenticity. So if Mallory or somebody changes the message that's encrypted with an NCPA block cipher mode, when Bob decrypts, he has no idea that it's been tampered with. And Mallory can do this in clever ways to maybe change the meaning of the message or just make it gibberish. But no matter what, Bob can't be sure that the message hasn't been tampered with. So we kind of glossed over it, but that's an important part of block ciphers is they have confidentiality, which is great, but they don't have integrity yet. So that's today's job. We have to start figuring out how to create things that have integrity. So before we do that, we have to first introduce another building block, which is cryptographic hashes. So we'll talk about those. And then we'll use cryptographic hashes to build our symmetric key integrity schemes, which are Max. And then if we have time at the end, we'll talk about authenticated encryption, which is how do I combine stuff from today with stuff from yesterday so that I get schemes that give me confidentiality and integrity and authentication. So then I can have all three. So that's the plan. So we're going to start with hashing. So hashing is kind of a side topic, but we're going to use it as a building block to create Max later. So I guess this is the best I could do with putting it on this slide. So the definition of a hash is, well, here's the hash function. So the input is an arbitrary length message M. So this message can be as long as you want or as short as you want. So hash functions take any length inputs. There's no limit on how long the input is. But the output is always fixed length. So if I input a 1-bit message, the output is n bits. If I input a 10-bit message, the output is n bits. If I input a 1 million bit message, the output is always n bits. So the output is always fixed. So sometimes you see it written like this for math people. So for a hash function to be correct, it has to be deterministic. Hashing the same thing 10 times is going to give you the same output 10 times. For efficiency, we're looking for efficient to compute. So again, generally we'll look for things that use bit shifting, XORs, things that are fast in a modern processor. And there are 3 security properties that we're going to dive into in a minute. So I'll just leave them up there for now. And the intuition for hashes is we're basically looking for unpredictable outputs. So there shouldn't be any pattern that, oh, if I change this in the input, then the output will change this way. So it should be so unpredictable that if I change 1 bit in the input, so if I just take 1 bit of the input and flip it from a 0 to a 1, the output is just completely scrambled. So the hash function should basically look like it's scrambling things with no discernible pattern. So you don't need this to be part of the theoretical definition, but the intuition is that we're basically scrambling up the inputs in a way that's very unpredictable. So one way you can also think about this is hash functions give us a fingerprint over the input. So a fingerprint is something that uniquely identifies you, right? So a hash function, the output of the hash function uniquely identifies what the input was. So one way you can kind of use a hash function is maybe to compare documents. So let's say Alice has a gigantic document, 1 gigabyte large. Bob also has this 1 gigabyte large document. And they don't want to have to send this document to each other and compare it and be like, well, the first byte matches, the second byte matches, the third byte matches, and they have to match a huge amount of data. They don't want to do that. So instead, what they're going to do is they're both going to hash the document to get a fingerprint of the document. So they take the 1 gigabyte hash and they use that as input to the hash function. And the output of the hash function is an n bit because it's always n bit output. And now Alice and Bob could compare their much smaller n bit output and check that they match. And remember, hashes are deterministic. So if I hash the exact same document twice, I get the same fingerprint twice. So if Alice and Bob compare their hashes and they realize it's the same, then they must have the same files. But if the hashes are different, then they must have different files. Because remember, if I change just 1 bit in the document, then the entire hash function looks unpredictable and different. So this is just one way you might consider using a hash. So then we talked about there are 3 security properties. So now we'll go through those. So the first one is a hash function should be one way. I guess the noun version of this is one-wayness. Sure. Sometimes it's called pre-image resistance. So the way pre-image resistance works is I give you an output of the hash. So I hashed something and I got this output and I'm going to give you this output. And I'm going to challenge you to find any input that hashes to this output. So I give you the output and your goal is to tell me, just give me any input that if I pass it through the hash, I get the same output. And the goal is that this is very hard. So with any reasonable amount of computing power, it's not possible to do this. So I give you the output, you need to find me an input that hashes to this output. And you can't do that. If you can't do that in a reasonable amount of time, then the hash function is one way. Now note that sometimes people think of this as, well, I give you the output, you can't tell me the input. So sometimes people think of it like that, but that's not exactly right because the adversary doesn't have to find the exact input you used to get this output. they just have to find any input. So it might be the case that two different inputs give you the same output. And if that's the case, then they can give you either of those inputs and it's fine. And in fact, I don't think we have to worry about this, but in theory, hashes have infinitely many inputs, right? Because the input can be any length, but the output is n bits, so there's only 2 to the n possible outputs. So by definition, there has to be multiple inputs that map to the same output. I think maybe we'll cover that in a little bit, but you don't have to worry about it too much. But the idea, again, is that I give you the output, and your challenge is to give me any input, doesn't have to be the one I used, that hashes to the same output. If you can do that, then the hash is not one way. If it's impossible for you to do that with any modern computing power, then it's not one way, or it is one way, sorry. The second property we look for is called second pre-image resistance. This one is almost the same, but it's just slightly tweaked. So before I said, here's an output, find me an input that hashes to the same output. Now, instead of giving you the output, I'm actually going to give you the input, and you have to find a different input that hashes to the same output. So it's the same thing as before, but instead of giving you the output, I give you the input, and you need to find me a different input that matches the output. And remember, if I give you the input, you can find the output yourself because anybody can compute the hash. So you can think of it like I'm giving you the input and the output together, and you have to find me a different input. It can't be the same one that hashes to the same value. And the third property we look for is called collision resistance. So again, kind of similar, but this one is even more broad. So a collision just says, find me two different inputs that have the same output. I think we talked about this just now, but is there a way to design a hash function with no collisions whatsoever? Well, not really, right? Because again, there are infinitely many inputs. Any length string is a valid input, but there are only a finite number of outputs because the output has to be n bits long. So by definition, there are more inputs than outputs. So you can't map every input to a unique output. You have to map multiple inputs to the same output. So by definition, hashes do have collisions. There's always going to be two different inputs that hash to the same output. But my goal is to say, given any modern computing power, you can't find one. So collision resistance says there's no way to find any pair of inputs that match. So remember, one wayness said, I give you the output, you have to find me an input that maps to this specific output. And then second pre-image said, I give you an input and an output, and you have to find another input that matches this specific output. But now collision resistance is more general. It says, I don't even care what output you pick. Just pick any output and find me two different inputs that collide. That's all you have to do. So you don't have to match what I give to you. Just find anything that collides and you win. And the goal is that this is not possible. So if the attacker cannot find any collisions in any reasonable amount of time, then it's a collision resistant hash function. Okay. What? Well, I'm pushing next and nothing's coming up. Oh, okay. I guess I screwed up the transitions. So you got to fade. Maybe if I was thinking I probably screwed up a couple of transitions that you were going to get, like the slides will it would tumble in or spin or whatever, but I guess you got a fade. Okay, so the observation here is that collision resistance is a little bit easier than second pre-image resistance. So collision resistance says, again, just find me anything that collides. But second pre-image resistance says, find me something that collides here. So here's the output, find me a collision right here. So by definition, collision resistance implies second pre-image resistance. So if I can't even find any output that collides, then there's no way if you tell me to find one right here, you're going to find it. So I can't even find, if you don't even tell me where to find the collision, I can't find any collision anywhere. Then if you told me to find one at a specific location, I can't do that either. So by definition, if it's collision resistant, it's also second pre-image resistant. And if you do a bit of CS70 calculation, I don't think you have to worry about the math too much, but you can also see that collision resistance takes approximately 2 to the n over 2 tries, but second pre-image resistance takes 2 to the n minus 1 tries. So collision resistance is easier than second pre-image resistance. So if I can't even solve the easy problem, I can't solve the hard problem either. So that's the intuition here. Okay. So there are a bunch of modern implementations of a hash function. So here they are. The ones that are kind of important are MD5 is a hash function you hear about a lot. A lot of people on the internet still use MD5, but in terms of security, it's really old and completely broken. So if you're looking for a hash function for secure purposes, you can't use MD5. It used to be secure, but people have done research on it and it's completely broken now. You can find collisions, you can reverse hashes, you can do anything. And in fact, you can even do fancy things like this GIF, please don't complain at me, one of those two. But this animated picture actually displays its own MD5 hash. So if I hash this picture, all the bits of this picture, I actually get this hash value. So not only can you create collisions, but you can also generate very fancy, elaborate hash collisions because MD5 is so broken. So you can predict, they can create this image to predict that it hashes to this value. So that's how insecure MD5 is. Then SHA-1 came out. This had 160-bit output, and it was completely broken in 2017. A random fact that I learned about SHA-1 was that the researcher who broke SHA-1, I think they're in the Philippines or something. They might be French, I don't know. But they have their last name is my first name, which is kind of crazy because I don't know anyone else with my first name. The only other person I know who's kind of like twins with me is some dude named Thomas Payrin, I guess, or Thomas Payrin, I don't know. But that person is the person who broke SHA-1, so and now you know. You don't have to know that for exams or anything, but okay. But yeah, SHA-1, even before 2017, people suspected it was broken, but my doppelganger from some other country did research on it and completely broke SHA-1 in 2017. So today, most people use SHA-2 or SHA-3, which are the modern standards. And I think that's basically all I have for examples. Another kind of unrelated attack in hashes is called the length extension attack. So I give you the hash, I give you the output. I also tell you how long the output is, but I don't tell you the input. So I just give you the output. Now, by all the properties by before, you can't tell me what the input was. You can't find another input that maps to this output. But if the hash is vulnerable to length extension, you can actually give me the hash of X concatenated with M. So the double Lenser concatenation. So you can extend the input for any M of the attacker's choosing. So again, you don't know the input, but just given the output, you can actually give me the hash of a different message that's valid. So it doesn't violate one way, it doesn't violate second preimage, it doesn't violate collision resistance, but we generally do not want hashes to be vulnerable to this because, again, if you give me the output and I can give you another valid output for your input concat with some other message, there are a lot of situations where you don't want this to happen. So SHA-256, which is the 256-bit version of SHA-2, is vulnerable to this, but I think SHA-3 is not vulnerable. So in general, if you do need hashes, SHA-3 is probably the way to go because it's the most modern secure standard. But a lot of people still use SHA-2, so yeah. Okay, so I think we are almost done with hashes. The one last thing we should show you is it's kind of a stupid or fun application of how hashes might be used. So here's your challenge. There's an attacker somewhere. They've stolen 150 million records from a website. Well, that's a lot of records. And they might be private records or something. And the attacker doesn't want to show you the records. But if you're a reporter or something, they want to prove to you that they actually stole 150 million records. So you're the reporter, you're writing an article about this hack and this attack, and the attacker comes to you and says, I guarantee to you I have 150 million records, and if you pay me, if the company pays me $1 million, I won't release them, or something like that. But the goal here is that the attacker could be lying, right? What if they didn't steal 150 million? Maybe they only stole 15 million, or maybe they stole 100, or maybe they stole 1. You don't know, right? So what if the attacker sent less and they just exaggerated the number that they sent to try and get more money from the company or something? So we, as the journalist or the reporter, need to figure out how the attacker isn't lying. But the attacker also doesn't want to prove it to us by sending us all the records because they're holding it for ransom, right? They want to force the company to send them $1 million to hide the records or something. So they don't want to give us all 150 million records, but they still want to prove to us that they own 150 million and they don't own like 10 million, and they're exaggerating. So how do we prove that they're not lying? Well, there's a very clever solution here, and the solution is to use the cryptographic hashes that we saw. So here's what we're going to tell the attacker to do. So we're going to say, hey, attacker, you need to hash all 150 million records and send us the 10 records that have the lowest hash value. So you hash all the records, they all produce different hashes, and you need to send us the 10 records that have the lowest hash value. And the idea here is that hashes are unpredictable. So the attacker has basically chosen 10 random records to send to us. And the hash forces them to choose a given subset of 10. So that's what the attacker is going to send to us. They're going to send us the records and the hashes, the 10 records and the 10 hashes that have the lowest value. Now, how do we know the attacker wasn't BSing and that they only had 15 million or 10 million? So what we can do is, we can check the hashes, first of all, and verify that they did send us the correct records. So we hash the record, make sure that it matches the hash that they sent. Then, and this part is the kind of clever part about this algorithm or this strategy, what we're going to do is we're going to say, well, hashes look random. So the 10 hashes that they sent to us are basically, if I had generated 150 million random values, these are the 10 minimum ones. So we check that the hashes match what we expect the minimum of 150 million random values to be. So this part is a little bit weird, but one analogy that might help you if you don't remember probability too well is, well, let's say I have a bin with 100 balls, and I'm going to pull balls out of the bin, and I'll look at the number on it. So there are 100 balls in the bin, they're numbered 1 through 100. I will pull a ball out of the bin, look at the number, and then put it back, and then take another one out, look at it, and put it back. And I'm going to keep track of what the lowest number I saw was. Well, so this bin has 100 balls. If I pull out just a single ball, look at the value, and put it back, and I track the minimum, if I do this once, the minimum is probably going to be something like 50 or 40 or 60 because there are 100 balls and all of them are equally likely. But if I pull 10 balls out and I look for the minimum, then the minimum is going to be a bit lower. It's going to be something like 10 or 20 because I pulled 10 balls out and I looked for the minimum. If I pull 100 balls out, now the minimum should be something like 5 or 4 because I tried so many times. And what if I pulled 150 million balls out and I put it back every time and I repeated this 150 million times? Well, now the lowest number is probably 1, right? I pulled 150 million balls out of this bin of 100 balls and I looked at all the numbers and I looked for the minimum. It's probably 1, right? The odds that you pull 150 million balls out of this bin and you never see a 1 is like astronomically small. So it should be 1. So if the attacker wanted to cheat, or if the attacker was lying and they had 15 million records, then we can use probability to calculate if you had pulled 15 million balls out of this bin or generated 15 million random hashes, you should expect this to be the approximate minimum. And if I generate 150 million, then the minimum should be this. And if what they send us doesn't match my probability calculation, or I calculate the probability and it's way unlikely, then I have a good idea that the attacker is lying. But if the attacker's probability matches what I calculated, then the attacker probably isn't lying. So you don't have to worry too much about this scheme. In hindsight, maybe we could have even just given it a blue background, but it's just an example of how, even if you're not dealing with cryptography and securing messages, there are actually a lot of other interesting ways you can use cryptographic hashes for your benefit. So yeah. Any questions on this one? Because it definitely is a little bit wacky or unusual, but yeah. Okay, if there are no questions, I think we're almost done with hashes. I think the last question we have to ask ourselves is, the whole goal of today's lecture is we're looking for integrity. So we have to ask ourselves, do hashes provide integrity? Well, the answer is, as often in security, it depends on your threat model. So it depends on who's attacking you and how. So for example, let's say Mozilla publishes a new version of Firefox, the web browser, and Alice downloads the executable to install and load Firefox. So she downloads the Firefox program. Okay, but she needs to be sure that she didn't download an attacker's executable before she runs it on her computer. She needs to make sure this is the real Firefox and not some attacker's tampered Firefox. So how can she be sure that nobody has tampered with this Firefox thing that she downloaded? Well, she can use hashes, right? So it's kind of the fingerprinting from before. When Mozilla publishes the hash, or when they publish this program, they will hash the program and then publish the hash onto their website. Now, when Alice downloads the large program, she can hash the program and it will output a hash. And she checks that her hash output matches the one that is on Mozilla's website. And if it matches, then she knows that her version is the same as the one Mozilla published. If the hashes don't match, then she knows that the one she downloaded does not match what Mozilla published. Okay, so she did detect tampering if someone tampered with it, but we had to assume something. I guess we should talk quickly about this first. And if the attacker wanted to create a malicious program that avoids detection, so Alice downloads a malicious program, but the hashes still match, the attacker can't do this. Why? Because it's collision resistant. So the attacker can't find two different binaries that match the same output. So if that's true, then the attacker can't even avoid detection. The attacker will always be detected. But for this to be true, we had to assume something. We had to assume that the website is secure. So the hash that's published on Mozilla is secure. Nobody tampered with the hash. So in this case, hashes did provide integrity, but we had to assume that the website hash wasn't tampered with. So if that's true, then we can use this strategy to provide integrity. So in this particular threat model, assuming that Mozilla is honest and nobody has hacked Mozilla's website, then yes, we can maybe say hashes provide integrity. So in this special scenario, maybe yes. And again, the thing we're assuming is that the hashes have been communicated securely. But let's say there's a different threat model, and this is the one that we're used to. And this is the classic Alice and Bob want to communicate over an insecure channel, and Mallory tampers with messages. So in this case, let's try again to use crypto hashes. And Alice sends her message, and she sends the hash of the message over the channel. And then Bob will receive the message and compute the hash and check that the hash matches. Okay, so does this provide integrity against Mallory? And remember, Mallory can tamper with anything over the channel. So does this still provide integrity? Yes, no, I don't know. Show me the answer. A lot of people said no, right? And the reason why it's no is because Mallory can just change the hash, right? So if Alice sends hello, Bob, and then the hash of hello, Bob, Mallory can just take that message, just throw it out, and then replace it with her own message that says, screw you, Bob, and then hashes screw you, Bob, and then that will be accepted by Bob because Bob will check the hash and they don't match. So Mallory modifies the message and the hash, and now hashes don't provide integrity. Oops. Okay, so the main problem here is if the attacker can modify the hash, then hashes don't provide integrity. The reason here is because hashes don't have keys. Remember how we said cryptographic protocols always start with a key and generally a secret key that the attacker doesn't know, but hashes don't have any keys. Remember, the argument is just an input. There are no keys. So because hashes don't have keys, any attacker can compute any hash they want. There's no limit to what an attacker can or can't compute. There's no key. If I want to hash a message, I can do so. If you want to hash a message, you can also do so because there's no key. So that's the problem with hashes. They kind of provide integrity if you can guarantee that the hash is secure, but if you can't, and in our Alice and Bob model, they don't provide integrity. So our next goal for today is use a hash to design a scheme that does provide integrity. Okay, how is everyone doing? Do we need a break? Should we just plow onwards? We have to finish Max, and then there's one small topic after Max. Any thoughts? Do we need a break? Should we just keep on going? Okay, we'll just keep going for a little bit. And then if anyone feels like they're collapsing under all the information and needs a break, you can just yell out something and we will consider a break. Okay. So we finished hashes, and now we're going to go back to build the scheme, and this one is going to be Max. So these are symmetric key schemes, and they provide integrity and authentication, but they don't provide confidentiality. So we're not looking for confidentiality today, just integrity and authentication. In the Firefox example, why not just put the code on the website? So why hash it? That's a really good question. I think the reason why is because if you put the code on the website, it could be a really big program, and maybe you don't have the bandwidth to host a really big browser program on the website. But the hash is a very small value, so you can just hash and compare that. So that's probably the main reason. But that's a very good question. If the program was smaller, maybe they could just put their program on the secure website. Okay. Cool. So back to Max. So how are we providing integrity? Now, we talked about this a bit 2 days ago. We talked about how you can put a seal on a message. So that's what we're going to try to do today. So a reminder, though, we're still in symmetric key. So again, the crypto gods have descended upon us and blessed Alice and Bob with their secret key, and the attackers do not know this key. And tomorrow, we're finally going to answer the question of how this happens. But for today, we're still in the symmetric key assumption. So like we said 2 days ago, our goal is going to be to attach some information to prove that the message came from somebody with the key. And if you don't have the key, you can't generate this information. So here's the diagram from a couple days ago, and it's basically what we're going to look at today. So again, the goal is Alice wants to send this message to Bob over an insecure channel, but Mallory is here, and she's going to try and tamper with the message. So she's going to try and change the value of the message. And our goal is for Bob to receive the message and be very certain that it's not been tampered with. So in the analogy, I guess, if you remember that, what Alice does is she takes her special tape that only Alice can create, and she tapes the message over with an envelope, or she seals it in an envelope and then puts tape on the envelope. And then she sends the envelope with the message and the tape over the insecure channel. And then if Mallory tampers with the message, what does she have to do? She has to open the envelope. And when she opens the envelope, the seal is going to break. Right? The tape on the envelope is going to break, and she can't retape the message. So when Bob receives the message, all he has to do is check, is the tape there? If the tape is there, then the message is good. If the tape is broken, then somebody has probably messed with my message. So in math, the way this works is there's a function called a MAC, or a message authentication code. And what we do is we take the message and the key, and we pass them through this function, and it outputs a tag T. So the T, this tag is kind of the seal on the message. So this is the algorithm. It takes a key, it takes a message, and it outputs a tag. I send the tag and the message over to Bob. So Alice takes the message and the tag, sends both of them over the channel. And Bob is going to recompute the MAC and check that it matches the tag. So Bob takes the verify algorithm here is you take the message, you compute the MAC again. So you use the key and the message and compute the MAC again. And if the MAC matches, then the message has not been tampered with. If the MAC doesn't match, then somebody has changed the message, because if this was the original message, the MAC would be the same. If this was a modified message, then the MAC would no longer match. So that's the high level idea. And again, if the MACs match, then we're confident that it hasn't been tampered with. If not, then it has been tampered with. Okay, we'll see if my voice doesn't blow out by the end of this. So formally, the definition of a MAC is an algorithm with 2 parts. So as usual, there's always a keygen algorithm. So we have to define what's the key? How do I generate the key? So that's the keygen algorithm. Then there's going to be a MAC algorithm. So it takes in the key and the message and generates a tag for that message. So the key is secret. The message can be as long or as short as you want. So you can do MACs on short messages and long messages. And the output is a tag, which is fixed length. So this hopefully sounds a little bit familiar, right? We just saw a function that inputs arbitrary length messages and outputs a fixed length fingerprint. So this should sound very familiar. The only thing that we're adding today to create a MAC is the key. Hashes didn't have the key, but they had the same input-output structure. MACs have an additional key, and that's where the security is going to come from. So there are, again, a bunch of properties. The important property for correctness is, again, same as the hash, it needs to be deterministic, because how is Bob going to verify? Bob is going to recompute the MAC and check that the tag is identical. So if I compute the MAC twice on the same inputs, I need to get the same output twice. There are some more complicated MAC schemes that are non-deterministic, but we're not going to worry about those for today. Efficiency, again, not too important, but just make sure that you're using things like bit shifting and XORs so that it's fast. Security will be defined with the game that we'll talk about, I think, right away. So here we go. So the properties of a secure MAC are that they're existentially unforgeable. It's kind of a fancy term, but all we're saying is that if you don't know the key, you can't create a tag yourself. That's all we have to say. So Mallory, when she sees the message and she doesn't have the key, she can't create her own tags. Because if she could create her own tags, then we're back in the situation with the hashes. All she has to do is change the message, change the tag, and then it'll check out. But if the MAC is secure and not forgeable, then Mallory can't forge a tag for her own message. So if Mallory's message is M prime, she can't create a MAC of M prime without the key K. Mallory also can't find two messages that have the same MAC. So those are the two high-level properties we're looking for. And again, just like in CPA, if I want to define a game, I can make this into a game. So here's what the game looks like. It's a bit simpler, but the idea is the same. So we have Mallory versus Alice today. Alice says, I have a scheme that's secure. My MAC scheme is secure. Mallory says, I don't think your MAC scheme is secure. I'm going to challenge you that your MAC scheme is not secure. So they're playing against each other, and we'll see who wins. So the CPA stands for chosen plaintext attack, which is, again, our model. So the idea is kind of similar. Mallory can send Alice any message that she wants and gets the MAC of the message back. So Mallory does not know the key, but Mallory can always ask Alice, say, encrypt this, or not encrypt, but MAC this, and Alice will send the MAC back. And she can do this over and over again to a reasonable limit. And then once Mallory is done playing with the hash function and she thinks she has some information about how it works or what the key is, Mallory will create a pair. So she'll say, here's a message and here's a tag. And this message can't be a message that she sent before. So this needs to be a new message. And the reason why it has to be a new message is because if it was an old message that she sent here, then MACs are deterministic. So if I MAC'd it twice, then it would be the same MAC. So it needs to be a brand new message that she hasn't seen before. And if she created a valid pair, so this tag is a valid tag for this message, then Mallory wins. She found a tag without knowing the key. If Mallory cannot do this, then she loses because it's not a valid tag. So if a scheme is in CPA secure, then no matter what Mallory tries, again, she can do something that has been defined. She can invent her own attacks. But if she cannot win with any probability, so today the probability of winning has to be 0 or negligible, then the scheme is EU CPA secure, existentially unforgeable. And the reason why today the probability of winning in this game is 0 is because we're not guessing between two things. So we're not coin flipping. We're just looking for Mallory to succeed at all. So if she can never create a valid pair, then the probability of her winning is 0. If she can create a valid pair without the key, then the probability that she wins is not 0, and the scheme is not secure. So this is the EU CPA game. I will pause if anyone has questions. Okay. So that's how a MAC is created. Now let's try and think about how we can actually create a MAC. So we'll create a real usable MAC. So the first one we're going to look at is called nMac. And the idea here is, well, we just saw hashes. We talked about how MACs are just hashes with keys. So let's create a hash with a key, and then we'll probably get a MAC. So here's one. It's called nMac. Again, the intuition is, we talked about hashes. Hashes look random. If you don't know the input, the output just looks unpredictable and random. So instead of just hashing the message, how about let's hash the key and the message together, and then the output, is the MAC. Well, if I hash the key and the message together, if you don't know the key, you can't hash your own messages this time, right? Because to hash a message with this, if you wanted to hash the key and the message together, you have to know the key. If I don't know the key, I can't hash the key and the message. So that's my intuition. So the keygen algorithm is a little bit different this time. For NMAC, at least, I need two different keys, K1 and K2. And the NMAC algorithm takes two keys. It's a little bit funky, but we'll fix this in just a moment. But the output is this. I take the second key, concatenate it. So I just take the second key, which is a bit string, and then take M and just attach them together. I hash that. And whatever this hash output is, I concatenate it with the first key, and then I hash it again. So I hash twice. And somebody out there has proven that if these two keys are different, just in one bit, doesn't have to be totally different, as long as these two keys are just a little bit different, NMAC is existentially unforgeable or secure. So the assumption is if the underlying hash function is a cryptographic hash function, then NMAC is secure. I just hash the key and I hash the message. And the intuition of why do I use two hashes, why not just use one, is the high level idea. You don't have to know the specifics, but it basically prevents length extension. Because if there was only a single hash, so let's pretend this outer one doesn't exist. If I only had this inner hash here, if I could see the tag for M, I could create a tag for M concat M prime with a length extension. So using two hashes stops the length extension attack. Okay, so this is NMAC. We talked about how it's a little bit clunky, right? So again, here's the algorithm. It's kind of clunky because I need two different keys. That's a little annoying, right? It would be nice if I could just use one key. And we said that the keys have to be a fixed length. They have to be the same length as whatever the output of the hash algorithm you're using is. So that's also kind of annoying. So if I just tweak NMAC a little bit, I can fix this. And the fix is called HMAC. So this is the real world industrial strength MAC function. This one is called HMAC. And again, the specifics aren't too important, but basically I just fixed the two problems before with some tiny hacks. So first of all, I would like to use keys that are as long or as short as I want, right? Because then I can use longer keys for security or shorter keys if I'm not as paranoid. So what I'm going to do is I'm going to take any random key and then convert it into the proper length. So if it's too short, just pad some zeros at the end. If it's too long, just hash it, and then it becomes n bits. Because remember, however long the key is, if I hash it, the output is always n. So I just take whatever key was given here, make it n bits. So this is my small, tiny hack to get around the fixed length key problem. The second problem is I need two different keys, but I only have one today. I only have k prime. So what am I going to do? I will just take k prime, XOR it with some random or some fixed value called OPAD, and then take k again, and then XOR it with IPAD, and I get two different values. Oops. Okay, so I think we talked about that. So again, the two things that I just hacked around here are I used k, which is arbitrary length, to get k prime, which is a fixed length. And then I used k prime, which is a single key, to get two different keys. So it's a little bit hacky, but it turns out that it works and is sufficient for security. So there you go. So OPAD or outer pad is just a random byte, 5C, that is repeated until it's the same length that you need. And then IPAD is just a random byte 36 that's repeated. And these are hard-coded. And in theory, these two could have been any number. So this could have been 5D or whatever, or this could have been 3-4 or something. But they just chose two different patterns to make the scheme secure. So it's kind of hacky, but the intuition here is that we used hashes to create a keyed function. And the keyed function had a little bit of the security proof secure version had a couple small problems. So I hacked around them by using one key to create two different keys. That's all. So that's HMAC. Any questions? I think someone pointed out that it's true that even if a hash function is susceptible to length extension, it could be by definition secure. It kind of depends on what your definition is. But if we're using the definition from this class that a hash function is one way pre-image resistant, second pre-image resistant, and collision resistant, you can be all three of those properties but still be vulnerable to length extension? But yeah, good question. Okay, so this is HMAC. There it is again in its color-coded glory. Someone asked, can you not hash a key if it's less than n? Yeah, that's true. I think if it was a shorter key, you could also hash it. I don't know why it's padding with 0. It might just be an implementation decision, but the specifics aren't too important, so we're not going to quiz you on how do you HMAC or something like that. But the idea is just the key can be as long or as short as you want, and under the hood, they just do a little bit of hacking to make it the right length. Yeah, good question. Okay, so HMAC is a hash function, right? It's just a hash of some junk that includes the key and the message, like we said, but it is a hash function. So that means that all the properties of a hash that we liked are still here for us. So for example, given the HMAC and given the key, I can't learn M because of the one-way property. I can't find the input and hashes to the output. If the underlying hash function is secure, the general idea is that HMAC doesn't leak information about the message. So I can see this hash output, but I have no idea what the input was. I can't even find what the original input was. Why? Because hashes are one-way, second pre-image, and collision resistant. So because it's basically a hash function, all those great properties of a hash from before carry over to HMAC. So I can't even figure out what the message was. And if I don't have K, I can't even verify that the tag is correct because I can't calculate this value. If I don't have K, I can't even compute this value, so that's cool too. Okay, so those are some properties of HMAC. Okay, so again, we've created our first MAC, and now we have to ask ourselves again, well, do they provide integrity? Do we solve our problem? And well, since we're almost short on time, I can just tell you that the answer is yes. So the attacker cannot tamper with the message without being detected this time. Now, do MACs provide authenticity? So authenticity, remember, says I can prove that this message came from its owner. And this property is closely related to integrity, but not exactly correct. And in all the past semesters, I think this slide didn't exist. So a lot of people asked us about this, and we decided just to answer it for you directly. So the answer is kind of complicated. As usual, it depends. And the answer is, if a message has a valid MAC, you know for sure that it came from somebody with a secret key, because the only people who can create MACs are people who have the secret key. If I don't have the key, I can't create a MAC, but I actually can't narrow it down to a single person because anybody could have computed this. So authenticity says it came from the person who claims to have sent it. So MACs are almost there. You can be sure that it came from somebody that had the secret key, but you can't narrow it down to exactly who. But if only 2 people have the secret key, so if only Alice and Bob have it, then you can say MACs do provide authenticity because, well, only 2 people in the world have this key. I received the message. It's not from me because I didn't write this, so it has to be from the other person. So if only 2 people have the key and they're talking to each other, then MACs do provide authenticity because it came from somebody with the key. There are only 2 people in the world with the key. It's not me, so it's got to be the other person. And finally, do MACs provide confidentiality? This one is no, right? So remember, we said MACs are only designed for integrity and authenticity. And one very easy way to prove this is to say MACs are deterministic. If I MAC the same message twice, I get the same output. So it's not NCPA secure. And in general, MACs are not really designed for confidentiality because you can't decrypt, right? MACs don't allow you to decrypt the message or recover the original message. So given a tag, I can't even go back to the message without the message itself. So MACs are not even designed for confidentiality. It just doesn't really fit in the confidentiality model that we defined. And in general, MACs just don't have confidentiality guarantees. You could design a MAC that's perfectly secure. It totally works. It's not forgeable, but it leaks all sorts of information about the message. So it's very possible to create an example like that. So integrity, yes. Authenticity kind of depends, but generally, yes. Confidentiality, no. Okay, so that's MACs. Yeah, so again, HMACs, they don't really leak information. So given the HMAC, you can't reverse it and go back to the message, but it's still a deterministic function. So no NCPA security, which is the property we want. Okay. that's it for Max. Any questions? Does someone want to demand a break? I think we might make it in time if we do take a short break. We can also not break and just blaze through it, and then we'll be done early. That's fine too. Going once, going twice. If nobody shouts break or chat throws break in the chat in the next like 10 seconds, then we will just keep going. Okay.
Yeah, let's take a break anyway.
Let's take a 5-minute break. Good idea. Okay, if you're on tape delay, we just time traveled 5 minutes and we are back with authenticated encryption. So we talked about symmetric key schemes that give us confidentiality. That's great. Then we talked about symmetric key schemes that give us integrity and authentication. That's great. But each one didn't give us one of the properties. So the last thing we're going to do before we're done with symmetric key for good is we're going to combine the confidentiality schemes and the integrity and authentication schemes so that we can have all three together. I want to have all of them. I don't want to have to pick. So the last goal for symmetric key is do some combination. So when you combine them, it gets a new vocab word. It's called authenticated encryption. And this is a scheme that gives me confidentiality and integrity and, depending on your threat model, because of what we talked about earlier, authenticity. So I can have all of them together now. There are two general approaches to doing this. One way is take our schemes from yesterday, block ciphers, chaining modes, then take our schemes from today, integrity, max, and combine them to create a scheme that has all of them. The second way is just to throw all of this out and start from scratch and design a scheme that has all three together from scratch. So those are the two general strategies. Okay, so I think we're going to start with the first one, and then at the end, we'll talk quickly about the second one. Why is it called authenticated encryption if authenticity is the one thing it doesn't always have? That's a good question. I think cryptographers just name things weird. Maybe Nicholas has a smart answer for why it's named this. Okay, I'll take that as a no.
What was that pause meant for me to interject? Integrity and authenticity are very closely related. So
yeah,
oftentimes if you have one, you have the other, but not always. And yeah, I don't know.
Yeah, I think people just haven't really defined these two terms concretely until recently. So sometimes people have used them interchangeably, but yeah. For this class, they do have specific definitions. Okay, so the first approach is take a scheme from yesterday, take a scheme from today, and combine them, and ta-da, we're done. But it's not so easy because crypto always has little edge cases and pitfalls. So the first pitfall for using the first approach to combine schemes is key reuse. So to combine schemes, we end up using two different algorithms at some point. For example, I use AES-CBC from yesterday and HMAC from today. So that's a combination of schemes. I need two different algorithms. And key reuse is using the same key in two different algorithms. So key reuse is not using the same key in one algorithm over and over. That's totally allowed. I can use the same key to HMAC a lot of different messages. I can use the same key to encrypt lots of different messages with AES-CBC. That's totally fine because the schemes are designed to let you use the same key over and over again on the same algorithm. But this is a different problem. This is saying I have two different algorithms, one of them for confidentiality, one of them for integrity, and I use the same key on both of them. That's key reuse. If you do key reuse, you can actually cause the algorithms to interfere with each other. They can do weird things that affect your security guarantees. So maybe AES-CBC by itself is secure, HMAC by itself is secure, but if I plug in the same key on both of them, they might do weird things that contradict and interfere with each other. This is especially true if they use the same underlying algorithms and blocks. So for example, there are some MAC algorithms that we haven't talked about that use block ciphers underneath. So if I use a block cipher-based MAC algorithm and I use a block cipher chaining mode to encrypt, then if I use them together, maybe the block ciphers start doing weird things like canceling each other out or tangling up and becoming complicated. And it's possible that if you reuse keys, you can actually lose the security guarantees that you had. So AES-CBC by itself is NCPA, HMAC by itself is EU CPA, but if I combine them with the same key, it's possible that you lose properties. So that's dangerous. And now, guess what? You have to start thinking about key reuse attacks. You have to think, well, AES-CVC uses block ciphers and HMAC uses hashes, and those are kind of different. So maybe I can go in and prove that they're separate. And I think those two are generally believed to be separate, so that key reuse doesn't totally break it. But guess what? You're still thinking really hard about this stuff, and you are going to get a headache, and now you have to think really hard. So how do I not think hard, which is what I always aim for? Just don't reuse key. So for every algorithm, pick a different key. So if I have two different algorithms that I'm using, then Alice and Bob will have two symmetric keys. One key is used for CPC mode only. The other key is only used for HMAC, and I don't use the same key. If I don't reuse keys, guess what? I don't have to think about key reuse. So if you want to key reuse, sure, have fun thinking about attacks. If you don't want to think about attacks, then just don't reuse keys, and you're good. Okay, so now that we have that out of the way, we're going to use different keys for this entire section. So that's what you'll notice. So here are our building blocks. So let's say we have an encryption scheme, a decryption scheme. These are from yesterday. Then we have a MAC scheme that's unforgeable. That's from today. Well, one thing I can do is just the simplest thing I can think of, which is I will encrypt the message, and then I'll MAC the message. Simple enough. And I'll send both of these over to Bob. Well, does this have integrity? It does, because the attacker can't tamper with the MAC. Does it have confidentiality? Yes, no. No, right? And the reason why it doesn't is because this MAC is not in CPA secure. We define that this MAC, even if it's HMAC or something and it doesn't leak information, it's still not in CPA secure because it's deterministic by definition. So this attempt not perfect because the MAC doesn't give us security. Well, one kind of clever idea I can fix this is, let's not MAC the plaintext. This MAC will leak information about M, whatever M is. So instead of MACing the plaintext, how about let's MAC the ciphertext? Well, now, again, I still have integrity because the attacker can't tamper with the MAC. That's good. I also have confidentiality this time. Why? Because, okay, true, the MAC could leak information about whatever you MACed. But guess what? If I leak information about the ciphertext, that's okay. The ciphertext is in CPA secure. So even if the attacker uses the MAC to learn about the ciphertext, you still can't tell me what the plaintext is. So it's okay. And the scheme does provide both integrity and confidentiality. So that's our first idea. The second idea is I say, wait a minute, this MAC is not secure because it can leak information. So I'm just going to encrypt it. I will encrypt the message and I'll also encrypt the MAC so that you can't decrypt and figure out what this MAC says. Because this MAC leaks information, I'll just encrypt it and then I'm safe. So again, integrity, yes, there's a MAC. So if you tamper, the MAC will show you that something has been tampered with. Integrity, yes. Confidentiality, yes. Why? Because everything is encrypted. So by definition, you can't decrypt anything. So those are the two general strategies for combining. Notice it's a little bit tricky. I can't just send the encryption and the MAC separately. I either have to MAC the ciphertext or I have to encrypt the MAC. So those are my two choices. They have names. So the first one is MAC then encrypt. You just saw this. You do the MAC first, then encrypt the message and the MAC together. That's called MAC then encrypt because I MAC the plaintext first, then I encrypt the MAC. The second one's called encrypted MAC. It's backwards. And this one says I encrypt first, and then I MAC the ciphertext. So those are my two strategies. Now, which one's better? So again, we have to think about edge cases. In theory, if you use them correctly, they're both good. And we just showed you why they're both good. But that's in theory. Now, of course, in implementation, things will screw up. MAC then encrypt has a very subtle flaw. It's very hard to see. But basically, the problem here is that if I need to detect tampering, I have to decrypt first, right? Because look at this thing. This has the encryption of the message in the MAC. So if I want to verify the MAC, I need to decrypt whatever was sent to me first, right? Alice sends something to me that's encrypted, and Bob will have to decrypt whatever Alice sent to me before I can verify the MAC. That seems like not a huge problem, but if you implement things wrong, basically the attacker can supply whatever they want. They can give you gibberish, they can give you something, and you always have to decrypt it because you can't check the MAC is correct until you've decrypted the message. That could be a very subtle flaw that could be exploited. So essentially, you're giving the attacker possibly the ability to do something like chosen ciphertext attack. So you remember from way back when we talked about threat models, a chosen ciphertext attack is an attack where Mallory or Eve can trick Bob into decrypting messages. So you think, wait, that's a pretty weird thing. How can you trick them to do that? One way you can trick them is if they're using MAC.encrypt and you can see the result of decrypting, then maybe you as Bob, or sorry, you as Mallory, you can send something to Bob and Bob will always decrypt it for you because they have to decrypt before they can check. So that seems like a problem. And in fact, this can cause side channel leaks. So remember, side channel says if you implement something incorrectly, you might leak information. So MAC.encrypt has this very subtle flaw. And because of that, we will always recommend that you use encrypt and MAC instead, because if you screw up, this doesn't happen. You will always check the MAC first. And if the MAC is already wrong, you'll stop and you won't be passing tampered data through decryption. Whereas MAC.encrypt, you're passing tampered data through decryption no matter what, and that could cause a problem. An example of a problem like this is called Lucky 13. This one was pretty famous. It happened on TLS, which we'll study later, but for now, all you have to know is it's a protocol for sending messages over the internet. It encrypts messages, it authenticates messages, and this old version 1.0, it used MAC.encrypt. This is the bad one, the one that we don't want. And what happened here, the encryption algorithm was CBC, and the problem here was that there was an attack that uses this insecure version of authenticated encryption to read encrypted messages. That's pretty complicated and you don't have to understand it, but the idea here was that you guess a byte of plain text, you change the ciphertext accordingly somehow. Now the MAC is not going to work because you changed it, you tampered. But the amount of time it takes to error is actually different depending on if the guess is correct. That's a little weird and that's an implementation problem. So if the guess is correct, then the MAC, I think the MAC still fails, but it fails slower. So one way you can maybe think about this is if I want to compare two strings, maybe I compare them one character at a time. I compare the first character. If they match, I check the second one. If they match, I check the third one. If they match, I check the fourth one. And then I check all the way through the string, right? If the first character is wrong, then I would check the first character. It's wrong. Boom, it's over, fail. So that will fail super quickly. But if my first 10 characters are all right, and the 11th character is wrong, then it'll check the first one, check, second one, check, third one, check, all the way up to the 11th character. That will take more time to check. So the timing attack is basically that, but a little bit fancier. So if something is wrong, it fails really quickly at the beginning. If something is wrong at the end of the message, it will take longer to fail. So that'll give you an indication that you guessed the first 10 bytes or whatever correctly. So you measure how long it takes to error, and depending on whether it erred really quickly or very slowly, that actually gives you some information about what the plain text was. That's really subtle and so hard to see, and even the TLS designers just missed it. So that was really tricky to find out. So what messed up here? What was the problem? Well, the first problem was the side channel attack. You had an algorithm, it was secure, and this MAC.encrypt in theory is totally secure. But because you implemented it badly, you gave the attacker a side channel. You allowed them to learn information based on the timing of the attack. And the other takeaway is just do not use MAC.encrypt. If they had used encrypt and MAC, I think this attack would not have worked because you were not decrypting whatever the attacker sent you. You would have just MAC'd and then errored. Okay, so that's Lucky 13. You get to try a kind of similar attack in Homework 2, so that's kind of fun. I think it's optional, but yeah. I think the first optional lab also lets you try this attack. But yeah, this is a real world attack that you can try with stuff from this class. Okay. Or a similar one anyway. That's our first approach. So either encrypt and MAC or MAC.encrypt, pick the good one. I always forget which one's which, but you can always refer back. The second method is called authenticated, but still authenticated encryption. But this one says, instead of combining schemes that do one or the other, I'm going to just start from scratch and design a scheme that gives me all three immediately. So just start from scratch and design the scheme. And then this design will give me all three together. This is usually called authenticator encryption with additional data. That's a lot of words. But again, all it is an algorithm that gives me confidentiality and integrity over the plain text. So I get both. And the additional data part just says, if I have some extra data that's not private, so maybe it's like, send this to Bob or some additional information, I can also get integrity on that. So that's just a bonus. But all you have to know is that it's an algorithm that gives me all of them together. So I get all of them. Now, if you use this correctly, that's great, right? I don't even have to worry about MAC then encrypt or encrypt and MAC or key reuse. I can just throw all that out the window because I just use this one algorithm and I get all three. That's great. So why not just use AEAD forever? Why even think about CBC and stuff? Well, AEAD is a single algorithm, so it has a very subtle problem, or not so subtle, which is that, guess what? If you screw up, you lose both. So that's not good. If you had used MAC then encrypt, maybe if you screw up one of them, you lose integrity or you lose confidentiality, but it's kind of hard to lose both. But because this scheme was designed to give you all of them together at the same time, if you use it wrong, then you lose everything together. So it's risky, it's like high risk, but if you use it right, then it's pretty convenient because you don't have to worry about all the MAC then encrypt and key reuse stuff. So high risk, high reward, I guess. It's up to you. If you do want to use AEAD, again, don't write your own because if you screw up, you lose everything. Instead, try using a crypto library that already has AEAD for you. That would be good. Here's an example of an AEAD mode. I don't understand how it works. I don't think Nicholas understands how it works, so we're not going to ask you to understand it. It's called Galois counter mode, and it is a block cipher mode, but it also has some extra stuff inside to give you integrity. As you can see, it has a lot of arrows and stuff that I don't understand, so I just leave you to marvel at how hard it is, but okay. So it's very fast. That's pretty good. It's very parallelizable, and it's fast. And again, we're using operations that are quick on processors. But again, the problem is it has an IV, just like block cipher modes. If you reuse the IV in a regular block cipher mode, you lose confidentiality. That's bad, but you might still have integrity depending on how you combine the schemes. But if you're in GCM mode and you reuse the IV, guess what? You lose confidentiality, you lose integrity, and you lose authentication. So it's very risky to use. If you had combined two different modes, this wouldn't have happened. So use at your own risk, and you have to be very confident you're doing it right. Okay. I think that's basically it. So in the last 7 minutes, I'll give you a quick summary. So first, we talked about hashes. The input is arbitrary length, so it can be as long as you want. The output is fixed length, so it has to be n bits long no matter what. For correctness, the output has to be deterministic, so hashing the same thing 5 times, you get the same output 5 times. The output should be unpredictable, so if you change 1 bit of the input, the output should change in unpredictable ways. There were 3 security properties that I want. One way that says, I give you an output. I challenge you to find me any input, doesn't have to be the one I use, just any input that hashes to the same output. You can't do that because the hash is one way. The second one is called second pre-image resistance. This one says, now instead of giving you the output, I'll give you the input and you can calculate the output yourself. But given the input, you can't find a different input that hashes to the same output. So you can't do that. And then the third one is called collision resistance. And this one says, I'm not even going to give you the input and output. You pick your own input output and find me any pair of inputs that are different that have the same hash output. So find me any collision and you win. And if you can't do that, then the hash is collision resistant. And remember, collision resistance is easier than second pre-image resistance. So if the hash is collision resistant, if the easy problem is impossible to solve, then the harder problem, second pre-image, is also impossible to solve. So collision resistance does imply second pre-image resistant. Some hashes, they might be secure based on these definitions, but they're still vulnerable to length extensions. So you can, if I have the hash of a message, I can actually create the hash of the message plus some other stuff that I pick. That's kind of dangerous. One fun way you can use hashes, I don't know if I said fun, but if you're a journalist someday, maybe someone sends you some hacked records, then you can tell them to hash their records and prove that they have 150 million records instead of saying that they have 50 million and they were lying. Now, hashes don't provide integrity unless you can publish the hash securely. So we talked about this. If you're Firefox and you can publish the hash on your website, you might be good. if you are Alice and Bob and you're communicating over the channel and Mallory can tamper with your hash, that is no good because hashes don't have keys. So those are hashes. That was the first half. Then we talked about MACs. MACs are really just hashes, but you throw in an extra key for integrity. So the input is a message and a secret key, and the message can be as long as you want. The output is a fixed length tag, the same length every time. The MAC is also deterministic. So if I MAC the same thing twice, I get the same output. And the way to check it is Alice attaches the MAC, and then Bob just recomputes the MAC and checks that it matches. And if the MAC is secure, it's not forgeable. So even if we can allow Mallory to trick Alice into creating messages, she can't create valid MACs herself. So even if we give her that chosen plain text attack style attack where she tricks Alice, Mallory still can't create valid MACs, and that's called existential unforgeability, EUCPA. And an example of a MAC algorithm that we showed you, there are lots of different ones, but the one we wanted to show you is called HMAC. And it's kind of a variation on NMAC, if you remember that. But basically, you take a key, you make it K prime by extending it or shortening it if you have to. So that's a little hack. We need two keys here. So I just XORed one with the O-pad, XORed one with the iPad, and I got two different keys. And then I just hashed the key and the message together, doing it twice to prevent length extension. So the double hash just makes sure I'm not susceptible to length extension. And by definition, this is actually proven to be secure. So as long as the hash function is secure, this is unforgeable. And we said that MACs don't provide confidentiality. The easiest way to think about this is just say they're deterministic, and deterministic schemes don't have confidentiality. The final topic for today, I have 3 minutes, is authenticated encryption. So these are schemes where I like confidentiality, I like integrity, I want to have both. So I'm going to try to design things that have both. The first approach is take a scheme from yesterday, encryption schemes, take a scheme from today, MACs, and combine them. And remember, there are two ways to combine. Either I MAC then encrypt, or I encrypt and MAC. But I always want to use encrypt and MAC because it's more robust to mistakes. If I screw up, I'm not allowing the attacker to decrypt anything that they want me to decrypt. So encrypt and MAC is the good one to use here if you decide to use one of these two. The second approach is say, I don't even want to use these schemes. I will design my own from scratch, and my own scheme will give me all three together. These are usually very complicated schemes, so we won't ask you to remember any of them. But they're great if you use them correctly because you use one algorithm, bang, you have everything. But the problem is if you use it incorrectly, guess what? You lose everything. So very risky. And I think one thing that we're missing here is that remember not to reuse keys. So you can reuse keys if you want to. I don't know why you do it, but you have to think very, very hard about attacks. So if you don't want to think very hard about attacks, just don't reuse keys. And then you can, so notice in this case, use K1 and K2. And I think that's basically it. There are a couple last questions though. Let's see. Why are you appending encrypt and MAC to the ciphertext? Oh, that's a good question. So how come I'm sending the encryption and the MAC? The reason why is because remember, MACs you can't decrypt the MAC. So MACs only have a forward direction. You can MAC a message and create a tag, but there's no such thing as decrypting the tag. You can check that tag's match, but you can't decrypt the tag or go backwards. So this MAC on this side, you MAC the ciphertext and you create a tag on it, but you actually can't retrieve the ciphertext from the MAC. The ciphertext does not give you information about the MAC. So I also have to send the ciphertext. So I send the ciphertext, and then I send the MAC of the ciphertext so that you can check that my ciphertext hasn't been tampered with. And yeah, one-wayness is one way to think about it, because if you're using HMAC, it could be another MAC, so maybe not. But if you're using HMAC, this is a hash, and hashes are one way, so I can't go backwards. But yeah, very good question. I should have clarified that. I think that's basically it. We have like 40 seconds left if anyone has last questions. Going once, going twice. And I think Nicholas is back next week. So if you're like, when is this guy going to leave? Well, I'll be gone soon, so don't worry. Okay, I think that's it. So I will stop the recording